Hi everyone, welcome back to Chem Help ASAP. Today we are introducing the topic of kinetics. Now in this video we are going to talk about reaction rates and look at data from two similar reactions and see how the rates of different species relate to each other. First, let's get a good working definition of what kinetics is. So kinetics is the study of rates of change of amounts of different species in a chemical reaction. I know that's a bit of a mouthful, so let's just continue to break this down into smaller bits. So if we're studying the rate of change, let's talk about reaction rate. So a reaction rate is a measure of how quickly or slowly a reaction occurs. And it is going to be related to the change in amounts of either reactants or products over time. So we can write a really simple equation for reaction rate. Here we go. So reaction rate is going to be the change of some species, X, over a change in time. Now let's put this in the context of a chemical reaction. So let's go super generic here. I've got A going to B. We've got two different reaction rates we can write for this. We can write the reaction rate of A is the change of A over the change of T. And we can also write the reaction rate of B is the change in concentration of B over the change in T. Now, something I'm sure you've noticed is I've put a negative here in front of the reaction rate of A, but there is no negative in front of the reaction rate of B. Why is this? Well, rates are going to be reported as positive numbers. And if you think about reactant A going to reactant B, the change in concentration of A is going to be a negative slope. It is going to be decreasing, and the change in concentration of B is going to be increasing. So reactants are going to require a negative sign in order to counteract that negative slope, whereas reaction rates of products are already going to be positive and they do not need a negative sign. Again, this is just to follow the convention that rates are always going to be positive. Okay, let's look at one of our examples. Our reaction is nitrogen gas plus oxygen gas going to nitrogen monoxide. Here is our table of data. We are measuring time and we're measuring concentration of nitrogen monoxide and concentration of nitrogen and oxygen. Here is our graph of this data. You can see nitrogen monoxide is increasing over time. This makes sense. It is a product. We're going to start with no nitrogen monoxide, and then we're slowly going to make more. And our reactants, our oxygen and nitrogen, are slowly decreasing over time. And for this particular experiment, we had the same concentration of nitrogen and oxygen to start with, so they track together on a single line. Okay, so let's write a rate for our products and our reactants. So if I'm going to look at the rate of the formation of my nitrogen monoxide, it is simply the change in concentration of my nitrogen monoxide over the change in time. However, here, when I write my rates for my nitrogen and my oxygen, you'll notice, first of all, they both have a negative sign. That is because they are reactants. Remember, rates are always reported as positive. And of course, you'll notice that they each have a 2 in front of this. Where is this 2 coming from? Well, it's coming from the stoichiometry of this reaction. Now, nitrogen and oxygen have a 1-to-1 stoichiometric ratio, so they are going to be the same. So when we have 1 mole of nitrogen and 1 mole of oxygen, how many moles of product form? 2 moles of product form. So the rate of increase of nitrogen monoxide is going to be twice the rate of decrease for our nitrogen and oxygen. Hence, we need a coefficient of 2 in front of our nitrogen and oxygen rates to make sure that they're equal to our product rates. But let's rearrange these rates so that they're written in relationship of reactants going to products. So I'm going to write it as rates of nitrogen and oxygen and then nitrogen monoxide. We're just going to rearrange these mathematically. Okay, so here are all of my rates now. I've put my nitrogen first just because my nitrogen was written first in the chemical equation. You can see that the rate of nitrogen and the rate of oxygen are equal to each other. Again, they both have negative signs because they are both reactants. Mathematically, you can see I've changed the 2 here to a 1, which means I now need a 1/2 in front of my nitrogen monoxide. Again, this is just mathematical manipulation. Both of these equations are true. But we can, of course, prove this mathematically. You don't have to trust that what I wrote down here is true. We have our data from our data table. Let's plug in some numbers and see if we can prove this is true. Okay, so I'm going to compare my rate of oxygen to my rate of nitrogen monoxide. Again, you'll notice I have my 1/2 in front of here. Now, I can choose any time interval that I would like. I just have to make sure it's consistent here. So my delta T needs to be the same for both my oxygen and my nitrogen monoxide. Again, I need to look at the same time interval. So I'm going to look at the time interval from 15 to 20 seconds. Okay, let's just plug our numbers in. So for oxygen, for your delta O2, remember when you have delta, this is going to be your final concentration minus your initial concentration. So for oxygen up here, I'm going to put my final concentration in first, then I'm going to put in my initial concentration. Here are my numbers. Again, you'll notice my 5.8 goes in first. The same is true down here for my time. I put my final time in first, then I put in my initial time. This is important that we get the final minus initial, again, because we are working with this negative sign in here. So make sure when you're doing rates and you're using the change, you're always going to do final minus initial. Okay, so this is the data for oxygen. Let's look at the data for nitrogen monoxide. So here are my concentrations of nitrogen monoxide. Again, I'm going to put my final number in first and my initial number in second. My time interval does not change. So here are my numbers here. You can see I put my 22.2 in first and then my 18.6. And of course, my delta T is identical to what it was for oxygen. It is very important when doing these calculations that you don't change up the time interval. So you can't compare rates from, say, 0 to 5 seconds for nitrogen monoxide to 15 to 20 seconds for oxygen. They must be the same time interval. All right, at this point, you can see I have a nice, clean mathematical equation. These are all very simple calculations. I just plug it into my calculator and let's see if I get them to be equal. And of course, yes, I get them to be equal. They're both equal to 0.36 molar per second. The great thing about all of these mathematical relationships, whether you're using this bottom one here like I did or this top one up here, is as long as you have the data, you can mathematically prove to yourself that you have written the correct relationship. Let's do one more. Okay, so we've got a new chemical equation. It's very similar, but it has a different stoichiometric relationship. We've got 2 of our nitrogen dioxide going to 2 of our nitrogen monoxide going to oxygen gas. Now, in this case, you'll see from our data table, we're starting with different concentrations. So we're starting with our reactant, and of course, we have no products. Our reactant is going to decrease, and our products are going to increase at different rates here. If I go to my graph, you can also see this is true. Again, here are my reactants. They are decreasing over time, and my products are increasing again at different rates. Well, why are they increasing at different rates? Because they have different stoichiometric ratios. In the previous problem, our oxygen and nitrogen had the same stoichiometric ratio. So each reaction is unique in terms of writing its rates and comparing the relative rates of, again, our reactants to our products. Okay, let's compare our rates. Starting with my rate of my reactant. So this is my nitrogen dioxide. Notice I have a negative in front of it and I have a 1/2. Again, this is because for 2 moles of nitrogen dioxide that decompose, I'm going to get 2 moles of nitrogen monoxide and 1 mole of oxygen. So writing the rate for nitrogen monoxide, I should have the same coefficient in front. And yes, you can see right here, I still have a 1/2. So the coefficients for both of these are the same because in the balanced chemical equation, they also have a 1-to-1 stoichiometric ratio. The main difference here is the sign. I have a negative in front of my reactants, and of course, our products do not need that negative sign. Okay, so then how do these compare with oxygen? Well, remember, oxygen down here, and it might be easier to see from the graph, has a very low rate compared to nitrogen monoxide and nitrogen dioxide. So it's going to need a factor of 2. Well, what is 1/2 times 2? It's just 1. So here is my rate of oxygen. So it, of course, has a 1 in front of it because it needs twice the rate of both of these guys to make it equal. Okay, of course, we don't have to write our rates like this. We can mathematically rearrange it just like we did with the other equation. So let's give our nitrogen dioxide a coefficient of 1 instead of 1/2. All right, so if I do that, of course, I still keep my negative. That doesn't go away, but now instead of having a 1/2 in front, I just have a 1. The same is true of my nitrogen monoxide, but now for my oxygen, you can see I have a coefficient of 2 because to make these all equal, oxygen needs a coefficient of 2 because its rate is less than that of nitrogen monoxide and nitrogen dioxide. And again, by a factor of 2. Okay, so I'm setting out to prove mathematically that my change in nitrogen dioxide is going to be the same as 2 times the change of oxygen. Again, I need to make sure my delta T is the same for both of them. So I am going to choose the interval from 100 to 150 seconds. Again, the interval doesn't matter, just as long as you're consistent between it. Remembering delta is final minus initial. My numerator here for nitrogen dioxide is going to be my 0.0055 minus my 0.0065. Again, final minus initial. And of course, my delta T is 150 minus 100. Don't forget to add in that negative. Don't drop that negative. For my oxygen, of course, I'm going to keep my factor of 2 here. And here are my 2 numbers here. So I'm going to do my 0.0023 minus my 0.0018. Again, the time interval is the same. And at this point, again, we have a very simple mathematical operation to do. You can just plug this in your calculator. And what you will find is these, again, equal 2.0 times 10 to the negative 5th molar per second. So when working these problems are asking to show what the relationship is between various rates of reactants to products. Of course, start with writing your rates out, but if you're unsure if you have the right ratio in terms of the stoichiometric ratio, use your data. Prove it to yourself mathematically that yes, you have the correct rates and you have the correct coefficients. This is why it is great to have data. I hope you found this video helpful, and thanks so much for watching.